Welcome back to another APES video. This one will be for Chapter 6, Modules 18 and 19, where we look into populations, how they function, and what affects them. From previous classes, I'm sure that you know about the different levels of complexity, going from individual to population, then later to community, branching out all the way to ecosystems, which are a bunch of different communities, and then that all adds up to make the biosphere. But again, we're going to be focusing more on that population level out of all of these different levels. First off, we want to look at population size, how many individuals there are in the area. We also want to look at the population density, how much space each of those individuals has, if they're very clumped together or if there's a lot of space between them. We want to look at the distribution, so again, looking back at density, they go hand in hand. Either they're clumped in small groups, they could be very random, where their distribution is all over the place, or they could have a uniform distribution where they're evenly spread out amongst each other. We also are going to care about the sex ratio, the males and females in a population, to look at their reproductive rates, and then also age structure, which will also help to see if reproduction is high or low based on how many old, young, and then reproductive age individuals there are in the population. Let's take a deeper look at population size. There are two different ways that population size can be affected. Those can either be density dependent or density independent causes. So density dependent factors or causes are factors that influence an individual's probability of survival and reproduction in a manner that depends on the size of the population. So this really is going to change based on if it's a small and not so dense population or if it's a larger, more dense population. Some examples would be the availability of food or other limiting resources, a migration, predation, or disease. Disease is one I think most people can easily think about. So if you have someone that's sick and not many people around them, which would be a low density, not many people are going to get sick. But now if you go to somewhere very busy and congested, like say an airport, like in the picture, there's going to be many people. It's going to be a very dense area. So disease is going to spread much quicker in that dense population. So it is dependent on how dense that environment is. On the other hand, for population size, there are density independent factors. These are factors that don't change based on the size of the population at all. These could be weather events such as a hurricane or a blizzard. These are widespread events that, again, are going to affect the population the same regardless of if they are densely packed or if they are spaced out from each other. This brings us to Module 19, where we're going to look at population growth models, where we're mostly looking at graphs. We're looking at graphs of how populations are growing, but we'll also be looking at survivorship curves, how populations are dying off. So it's mostly reading graphs and interpreting what is happening to these different populations over time, and we can extrapolate out from that what's happening and why. There are a few terms listed in this slide. The mathematical exponential growth model is not something that you need to be able to use, but it's something you need to be able to read and understand. The two that I'd like to outline here, though, are the population growth rate and the intrinsic growth rate. So population growth rate is simply the offspring that an individual can produce in a time period minus the deaths of the individual or its offspring. So this is just looking at the net difference in births and deaths, right? That will give you the growth rate. The intrinsic growth rate is a little different. It's the maximum potential of growth if you have unlimited resources under ideal conditions. So this would be like saying if you could have as many children as you wanted because you have infinite money, how many could you have? Versus, well, people usually have about 2 or 3, 1, somewhere in that range. So looking at the intrinsic growth rate is very different than looking at the regular population growth rate. This is going to play heavily into the two graphs that are in this chapter. The first one we'll look at is the J-shaped curve, the curve of the exponential growth model when. So this is that J-curve model. You'll see that it is an exponential graph with that very sharp increase after that slow lag period at the front. And it says, the exponential growth model, when populations are not limited by resources, their growth can be very rapid. More births occur with each step in their time, creating a J-shaped growth curve. So this is one of those words and graphs that you need to be able to recognize. Now the thing is about exponential growth is that it does occur, but it doesn't last forever. We don't live in a world of infinite resources and infinite space. So we call these limiting resources at some point, right? Resources that a population cannot live without and occur in quantities lower than the population would require to increase in size. They are literally limiting the population. And then once they hit that limiting resource, once they cannot use up what they need to in order to grow, we call that the carrying capacity, or as written, K. Again, this is the limit of how many individuals in a population the environment can sustain. In a sense, the carrying capacity is the cap of how many individuals can live in that area where no more can live. We'll see what happens when they overshoot that carrying capacity. So the more realistic model that we see in most things is this logistic growth model that takes into account the limiting factors, the carrying capacity, and is in a sense incorporating those environmental limits. So the logistic growth model, a growth model that describes a population whose growth is initially exponential but slows as the population approaches the carrying capacity of the environment. So you have that boom, you have that growth, and once they finally hit that limit, they're going to stabilize. We will see the S-shaped curve, the shape of the logistic growth model when graphed. So as you can see in this graph, it looks very similar to the J graph, the J curve. It starts off with that lag period where it's not experiencing much growth. It has extremely fast growth with its exponential curve, but then it begins to slow as things start to use up the resources that are available to them. It will eventually fall down to zero growth, as you can see with that stabilizing at the dotted carrying capacity, and it'll stay around that area for as long as that population doesn't have any disturbances. But in real life, disturbances occur. So if food becomes scarce, other conditions change, a population can experience fluctuations. For example, you could have a huge hurricane that knocks the population down all the way back to an exponential part of their growth where there's a lot of resources, but their population's so low that they can just keep reproducing. So we can see that it doesn't stay exactly on that carrying capacity forever. But the more minor fluctuations we call overshoots and die-offs. So an overshoot is when a population becomes larger than the environment's carrying capacity. They'll rise above it, and then afterwards you have them above the carrying capacity. Well, they're not getting food, they're not getting the things they need, so they're gonna die. That leads to the die-off. Die-off is a rapid decline in a population due to death. So if they're not getting the food that they need to survive, you're gonna have a bunch that die off, and you'll see in the next graph that you'll have an increase from the overshoot and a small die-off going underneath carrying capacity, and it will fluctuate around that level continuously unless there's a larger disturbance. Here's a more zoomed in graph of the population, and you'll see the carrying capacity is again noted by the dotted line. The up and down motions there are those overshoots and die-offs, and you'll see how one leads into the next. So it fluctuates up and down in a cyclic fashion. Another thing that could vary between different populations is their reproductive strategies. This is going to lead to them being at different points in that graph and perhaps even have different fluctuations. K-selected species and R-selected species are the two reproductive strategies we'll talk about. K-selected species are a species with a low intrinsic growth rate that causes the population to increase slowly until it reaches that carrying capacity, so they are not as dynamically changing. R-selected species are very different. A species that has a high intrinsic growth rate, which often leads to population overshoots and die-offs. So this one will have much greater fluctuations around carrying capacity, and they'll also, since they have a high intrinsic growth rate, recover very quickly as well during that exponential growth. Looking at some of the traits between the K and R selected species shows that they are very much opposite of each other. Lifespan: K selected species are long-lived, R selected species are short-lived. Time to reproductive maturity: how old do they have to be before they can reproduce? K selected species, a long time. R selected species, very short time. Number of reproductive events: few for K, so they're not having many periods of having offspring, whereas R selected species have many. So you can probably think of a few different things that fit these K and R selected species. For example, flies or other things that reproduce very quickly, even mice, would be R selected species, whereas something like an elephant or a panda would probably end up being more of a K selected species. The last thing we'll talk about is survivorship curves. These are graphs that represent the distinct patterns of species survival as a function of their age. So there are three different ways this can go. Either something can be a type 1, where it is going to have a pattern over time where there is high survival throughout most of its life, but then individuals start to die in large numbers as they approach old age. So really there's a huge drop-off when they get to their old age, like humans, for example. Type 2 is where you're not going to have any particular point in their life where there's a drop-off. It's going to be a stable death rate throughout. This will be something like a squirrel. And then type 3 survivorship is going to be where there is going to be a low survivorship early in life, with few individuals reaching adulthood. This is going to be something more like the fly, where they have thousands of eggs and only a few of them will grow to be full adult flies and reproduce once again. So you'll notice that the K-selected species are more typical of the type 1, right? They have more care for their offspring, they have less offspring, so they tend to have offspring that live throughout their early years, and then they'll eventually die off in old age. The opposite is true with the R, where they're having that die off in the beginning, and they're also having so many offspring that they are going to have many die. They aren't caring for them. It's more of a have many children so that they can survive to old age strategy. So both the type 1 and type 3 go with K and R. But in nature, nothing is perfect. So there is that type 2 and things that are between these different types for different specific organisms. But these are the three that we outlined to make things a little bit more simple.